from Technion. And first of all, I'd like to thank the organizers for inviting me to, for giving me an opportunity to speak in this valuable conference, valuable workshop. And actually, I'd like to ask for your understanding that the title of my talk is actually changed so that some recent progress in our work is reflected in this new presentation. So I'm going to talk about breakdown of the hydrodynamic limit for extreme current fluctuations. And this work is now in on progress in collaboration with Yarik Kafri and Vivian Lecomte. So first of all, I'd like to briefly talk about the current fluctuations in the hydrodynamic limit. So typically, as the simplest example of non-equilibrium system, we typically think about a system coupled to two particle reservoirs. And if there is some chemical potential difference across this system, then there is a current flowing through this system, which we can measure by observing a flux of particles at a certain cross-section of the system for a long period of time. And then you can ask about how rare are large current fluctuations, which are encoded in this large deviation principle, so that the large deviation function or the cumulant generating function, which are related by this Legendre transformation, has all this information about large current fluctuations. But now, we often assume that this system is in the hydrodynamic limit, so that in the limit that the microscopic units in the system, there are lots of microscopic units in this system, so that this L, which is the number of such units, goes to infinity. We assume local equilibrium for small subsystems of system, and then we do diffusive rescaling so that the length scale and time scales are rescaled with this L parameter. And then you can assume the system is in the continuum, and we can describe the fluctuation in the system by this Ramanujan equation, which is basically a continuity equation of fluctuating current. And the important thing here is that the noise here is a microscopic origin and it is small in amplitude. So using this small amplitude of noise, we can actually solve this system in a quite simple way. So actually there has been some microscopic approaches which start really from the matrix product ansatz and try to calculate this current large deviation function by taking this large L limit very later in the process. But also we can just start from this fluctuating hydrodynamics and then try to develop a saddle point approximation which pretty much simplifies the problem. Now let me briefly introduce this macroscopic fluctuation theory procedure of calculating the current fluctuations, because I'm going to repeat this structure again and again throughout the presentation. So we first express this cumulant generating function in a path integral form. And then we introduce some extra conjugate field rho hat so that we can replace this delta functional in the path integral by a exponential factor. And then we average over this fluctuating current. And finally, we can get some sort of expression for the action with this large parameter L coming in front. And using this largeness of L, we can do saddle point approximation. But eventually, this cumulant generating function has a form of some action from which we can develop some least action principle. And this function h, which is a function of this rho and rho hat, becomes a sort of Hamiltonian, so that we can treat this density profile rho as position variables and the conjugate field rho hat as momentum variables. And actually, if you compare between the original fluctuating hydrodynamics equation and this equation for the density profile, then you can see that this rho hat, which we introduced during the process, is actually noise realization. Now, how do you obtain the current fluctuation function, cumulant generating function from this structure? We can assume that the minimizing solution is actually stationary in time, so that the current flowing through the system doesn't change and is divergence free, so that we can keep all these rho and rho hat profiles constant in time. This is not an always true statement, but at least for this kind of open systems, I haven't seen any like examples where this goes wrong yet. So let's say that we cross this. And now we can evaluate the Hamiltonian from this stationary solution, which we also call optimal profile because we assume this to be optimizing this section. Then the current cumulative function is actually nothing more than the value of the Hamiltonian at this optimal profile. So basically, we have this structure. We start from fluctuating hydrodynamics. We get effective Hamiltonian from the certain point approximation. We get stationary solution for the Hamiltonian equations. We get optimal profile and then use it to evaluate the current cumulative energy function. Now, some authors have studied this kind of system for like quadratic mobility coefficient, and they obtained pretty much a general expression for the current cumulative generating function. And now for the symmetric exclusion process type of system, we get like Gaussian tail for the large deviation function of current, and for the KMP type of model, we get like exponential tail for the large deviation function. But in any case, what you can see from this cumulative function is that it has this vector of 1/L in front. So in any case, if you try to obtain the average current corresponding to a certain value of this Lagrange multiplier, then it is always going to be proportional to 1/L. This actually means that if we stay in the hydrodynamic limit, then the only kind of flux that we investigate is those which is actually have the order of gradient. So we can naturally ask some questions. So how can we study even larger, greater current fluctuations that is greater than this order of 1/L? And if we really study these kind of fluctuations, then the tail behaviors show some characteristics of a non-hydrodynamic limit. And actually, since it is difficult to study this kind of system from scratch, from the microscopic details, we want to develop a sort of alternative saddle point approximation. And this means that we have to find a sort of large parameter which doesn't lead us to the hydrodynamic limit, but it somehow is able to recover the hydrodynamic limit given some appropriate conditions. And then we should be able to calculate the current cumulative function easily from this large parameter. So throughout the rest of the talk, I'm going to describe this limiting process we designed, which is we call large N limit. And then we are going to study current fluctuation of the SEP-like model and KMP-like model using this limiting process. And then we are going to discuss how these two kinds of models differ from each other. So to motivate this limiting process, let us just think again about this hydrodynamic limit, how it actually consists of two different procedures. So first of all, we divide the system into subsystems, which are by themselves quite large, and each of them is in local equilibrium. And then we think of the limit where there are a huge number of such subsystems in the system, and then take a continuum limit. So there are among these two limiting processes, we can just take the first step and leave the second step untaken. This is our idea for developing our limiting process. So as an example, let's think about this symmetric exclusion process. Let us assume that some bonds of this system are far slower than the others. That between these low bonds, we can set up some imaginary boxes. And for each box, we can assume that the configuration very quickly relaxes to equilibrium, so that any configuration tipping the number of particles in this box are equally likely. And now let's think about these two sides, which is on the last side of this first box and the first side of this second box. And hopping rate, effective hopping rate between these two boxes will depend on whether the probability that this side is filled and this side is empty, for example. And using the property that all configurations are equally likely as long as they keep the number of particles in each subsystem constant, and we can actually see that hopping rates are actually proportional to the product between the number of particles in one box and the number of holes in the other box. So basically, we can do a sort of coarse graining, and then we define this system as a one-dimensional system of huge boxes with the hopping rates defined by these products between number of particles and number of holes. Now we have a sort of master equation for this system. And although this system doesn't obey any Ramanujan equation, we can still try to formulate the field theoretical representation of this system. Actually, the process is outlined in this paper by Lefebvre and Brioli. And in order to introduce a steady point approximation, we actually introduce this kind of scaling scheme so that the number of particles is rescaled to the density of each box, and the time is slowed down to account for the relaxation time scale of the system. So actually, if we go through this kind of rescaling scheme under the assumption that this parameter n, or the capacity of the site n, is large, then we can obtain a form of action which enables the saddle point approximation. If you look into more details for these kind of expressions, then this function h, which was in the original action, has all these kinds of expressions in terms of dense particle numbers. But if we introduce this rescaling, then it can be expressed in terms of density field variables. And actually, we can check that if the system has lots of boxes and nearby boxes have very small difference between each other, then actually we can, from this Hamiltonian, we can reconstruct the Hamiltonian for the symmetric simple exclusion process in the hydrodynamic limit. So actually, this shows that what this limiting process that we have defined is kind of in the intermediate regime, which is not yet in the hydrodynamic limit, but can be reduced to the can be restored to the hydrodynamic limit given appropriate conditions. So basically, we have fulfilled two of our original objectives for designing a limiting process that suits our purpose. Before moving on, I want to point out that this kind of limiting process is not actually what we have first proposed. It has been used in other contexts, including this study on population dynamics by Baruch Merson and co-workers. And also this kind of scheme has been briefly touched upon in this paper about spin J representation of SEP and KMP processes. And in this particular paper, their spin parameter J actually corresponds to 1/2 of our large parameter n. And they also take the limit of this going to infinity. And now I want to turn to the final objective of our study. So we can calculate the cumulative function from this Hamiltonian we obtained for this SEP-like model. We go through basically the same process that we used for the continuum case. And then we can obtain, actually, using the stationary saddle point assumption and using some ansatz inspired by the continuum case, we can obtain an exact expression for the Ramanujan generating function, which looks like this. And actually, this implies that the tail of the large division function is actually J log J, which is actually broader. Which is broader than the result obtained from the hydrodynamic limit. And thus we can obtain this auxiliary variable, which gives dependence on the Lagrange multiplier and the boundary conditions. And actually, this omega is common for both discrete case and continuum case. Now here I'm showing you some numerical plots, not actually exact, but I mean drawn by Mathematica, comparing between these two different kind of limits. So the dashed lines correspond to the hydrodynamic limit, and the solid lines show the large N limit. And you can see that if we fix the Lagrange multiplier, then as we increase the system size, then you can see some convergence between these two limits, which goes as L to the minus cube. But if we rescale this Lagrange multiplier by L, and actually this convergence disappears. This is clearer in this plot. Depending on this exponent alpha, which gives us scaling with the system, this parameter L, then like above this exponent 1, you get this divergence between these two different kind of limits. So we can actually find out that the non-hydrodynamic behaviors are observed where this scale linearly is L or the current being like stronger than order 1. So actually this is something of something that is not really easy to guess naively, because between this order of 1 over L and this order of 1, there's lots of intermediate regime, but we are having this breakdown of non-hydrodynamic behavior only for order of 1 current and above. So before trying to answer this question, let me just briefly go over a different class of model. So SEP-like dynamics was given in terms of this repulsion between nearby boxes, but now we introduce an alternative dynamics which gives attraction between the particles in the nearby boxes. And if we have attraction, then there's no longer any excluded volume repulsion. So there's no bound on the number of particles in each box. And the occupancy of each site can be actually much, much larger than this parameter n. So this allows us to consider the limit where the overall level of population in the system scales as n squared. And we can use this n squared scaling to introduce density variables and introduce a sort of somewhat different kind of limiting process for the system. And if we look at the effective Hamiltonian resulting from this process, then you can actually see that in the continuum limit, this gives us a Hamiltonian corresponding to the KMP model. Now, using a similar procedure for like SEP, then we can calculate the cumulant generating function. It has a very similar form, but with opposite signs and different auxiliary variable omega. And if we plot this cumulant generating function, we find out that the domain of this function is actually bounded by the boundary reservoir values. So again, we see convergence between these two different kinds of limits over this entire domain. And since this domain is completely bounded, it's simply impossible to find any scaling limit where these two different limiting behaviors become different from each other. So we see that hydrodynamic and non-hydrodynamic regimes are actually undistinguishable for KMP types of dynamics. So basically, there's a drastic difference between these two kinds of models, and it's natural to ask why they are so different. It seems that the optimal profiles supporting these current fluctuations had the secret. So if we look at the density profiles and momentum profiles supporting a certain large quantum fluctuation for the SEP-like model, then we actually see that due to the limit of capacity for SEP, this density profile is actually quite bounded, and it's becoming actually flatter and flatter as we increase the current. On the other hand, this momentum profile is increasing in slope as we increase the current. And in fact, we can find the scaling data class which describes how the slope is increasing as we increase the current. So we can actually find out that the large current for this kind of system is supported by this large momentum gradient here. Which scales like L to the alpha minus 1, where when this Lagrange multiplier scales like L to the alpha. And this gradient becomes small only when this alpha is greater than or equal to 1. So less than 1. So actually alpha equal to 1 is the borderline for small gradient. And this is why we find out this scaling regime for the breakdown of hydrodynamic limit for SEP kind of dynamics. Meanwhile, for the KMP-like model, as we increase the current, what we should see is that this density profile is rapidly growing in the middle. And in fact, if you compare between the contributions to this current fluctuation, then we see that the largest contribution actually comes from this high density value rather than any of these gradients. So it is actually some non-gradient component that is supporting this high current value. So having a extreme current doesn't necessarily mean that we are having a large gradient in the system. So this is, and hydrodynamic limit breaks down only when we have like current being sensitive to large gradient. So for KMP type of systems, they are particularly blind to this large gradient in the optimizing profile. So they still keep the hydrodynamic properties in terms of current fluctuations. So let me summarize our findings. We formulated a large N limit to investigate the possibility of non-hydrodynamic tail behaviors or current fluctuations. And under the assumption of stationary saddle point solutions, we obtained the exact expressions for current cumulative functions. And we found out that some reasons for these two models showing very different kinds of behaviors. And for future works, we need to check whether this stationary saddle point solution is really rigorously well established for these kind of systems. And also we believe that this large N limit is actually useful for making minimal models of non-equilibrium systems, which has smaller dimensionality than the hydrodynamic limit. And we have actually found out that this omega, which is a common, this omega, which is an auxiliary variable for the cumulative function, is common to all number of, common to the hydrodynamic limit and is also to this large N limit. So actually we can find this omega even by studying like one-dimensional system by solving this Hamilton's equation. And it remains to be seen whether this kind of simplification is also present for other kinds of more properties of these non-equilibrium fluctuations. So thank you for your attention.
Any question, comments?
So maybe this was not the purpose of you showed. At some point you showed this coarse grain model.
Yes, yes.
So are you also doing simulations with this coarse grain model?
Not really yet.
Because it might be interesting to see how it behaves with comparison, to the atomistic one as a suggestion to, when you want to calculate thermodynamic non-equilibrium quantities, you do it with this coarse-grained dynamics rather than atomistic ones. Since it seems that from your theory you could control the error.
Yeah, sure. Thanks for the suggestion.
Okay, thank all the speakers of this morning, and we resume at 4 o'clock this afternoon.